Hello community, so great that you are back. It is July 2025 and you ask, hey, what is the best combination? How can we combine here the power of a large language model with a knowledge graph with domain-specific knowledge? And we have here the combined power of a multi-agent system. How do we combine it? What is the best knowledge? What is best practice today in AI if you really want to build systems? Now we have some beautiful new publication, July 3rd, 2025, by Emory University and Stanford University, and they show us here how it is done. Real nice, and they say, we do now a knowledge graph enhanced reasoning approach that improves here our LLM-based diagnosis prediction through a multi-agent architecture. So we have everything we need. Our knowledge graph, our LLM-based prediction, and we will use for this a multi-agent architecture with multiple cores here of our agent, multiple LLMs. And you might say, why? We have so powerful LLMs, no? And here the authors here from Emory and Stanford tell us, well, LLMs still face significant challenges. LLMs lack structured medical reasoning capabilities, meaning LLMs are unable to systematically process and infer a relationship between medical concepts in a way that aligns with human clinical decision-making. LLMs are susceptible to hallucination, and this poses here serious concerns in high-stakes clinical environments. Plus, they tell us LLMs are sometimes quite useless in their prediction, and we have to make sure reliability and clinical applicability is there. So LLM need external guidance through structured knowledge integration. Now, this is not just about medical. Go for finance, go for physics, go for engineering, whatever you like. This here is a general recipe. So what we need a structured knowledge integration, and you think about a knowledge graph, of course, because here we have dedicated domain knowledge, and in our case is for medical. Now, you can take here a knowledge graph out of the shelf. Yeah? Available IBKH integrates your data from various biomedical knowledge graph. You have almost 2.4 million entities across 11 categories: drugs, disease, symptom, genes, pathways, plus 48 million relationship triples. So this is a great way to start. There's a lot of basic information available for you. Here you found a publication and you notice, oh, it is from 2023. So maybe it is not here containing here the latest research data or the latest molecular compounds or the latest relations or the latest, you get the idea. So what we do, we can update a knowledge graph, no problem at all. And I was asked to start here real easy and explain this in a simple way. It's a little bit of a challenge, but okay, I try my best. So you start here with huge medical text, all the medical textbooks or all the medical latest publication, or if you're in finance, the finance publication, you get the idea. And then you remember we have a transformer block. And now we need both sides of the transformer, because you remember on the left side we have the encoding part of the transformer, and on the right side we have the decoding part of the transformers. Now the encoding part creates a beautiful mathematical vector space where the linguistic closeness is simply mapped to the spatial closeness in a very high dimensional vector space. For the classical BERT system, it's about 1068 dimensions or something similar like that. For sentences, we create a sentence BERT, and if you want a fast search methodology, I think cold BERT is still one of the best ways to go. But on the other side, and you know this, no? Here we have our beautiful GPT systems, not the BERT system, the GPT system where we have multi-head self-attention with rope, positional encoding, and the same thing is happening here, and the goal is here a next token prediction. Now you understand here, it delivers something completely different, and we will combine here this to have a model. But we not just combine these two, but we need a third element. Yes, of course, the structured knowledge integration of a knowledge graph. So in the study, they go here with off-the-shelf standard knowledge graph or you have any other knowledge graph, whatever database you have, Amazon, Neptune, or whatever you like. Just go with what you are familiar with. So now it is interesting, because now if we say, okay, this is now 2 years old and we want to update this with the latest knowledge, it is also rather simple. You remember here, in the case of here sentence BERT or contextualized late interaction over BERT, the knowledge is in the geometric relationship between our vectors. And this vector representation is learned simply from the statistical patterns in our vast amount of text. And we will use this now also for the update process. And yes, of course, so we take here a classical BERT system, and then we will fine-tune it for a highly specialized high-performance tool. So we will have to have new data, so the latest publication of the last 2 years, for example, to update here this knowledge graph. And here you fine-tune BERT with your domain-specific vocabulary, with your domain-specific new technical terms, and with your new entity types that might emerge here in the knowledge graph. So, great, fantastic update, absolutely what you want. So you have now a beautiful, powerful NER engine. Remember, you can use BERT here as a cross-encoder. And if you have the BERT architecture with a token classification head on top of, you have a real powerful NER engine. So therefore, you can extract now all the entities from all your new documents, from all the new research paper, and therefore you can just update your knowledge graph in a very simple way. Yes, there are other more advanced ways, but hey, this is a simple and straightforward way to do it. Now, in our publication here from Stanford, they use here SAP BERT. SAP BERT is, I'm sure if you're familiar here, from 2021, quite an old workhorse here in the medical domain. And here the publication, Self-Alignment Pre-Training for Biomedical Entity Representation, is also available. But notice that we have here different elements. No? We have here a BERT system with a high-dimensional vector space. We have a knowledge graph that is per definition, has no definition, whereas I draw here two-dimensional pattern. And then we have, of course, multi-agent that connects all of this. So and the question is now, how can a multi-agent configuration work? What should we do? What is the complexity of our agents? Because we know an LLM is simply not able to do this alone. We have to reduce the complexity. We have to split up the complexity in simpler tasks and in a simpler architecture configuration. So we will use multiple agents. Now, just to show you on the interplay between our SAP BERT and our, for example, triplets here of the medical subject relation and object triples, how we do this, a simple example. Let's say in our dossier we have now for a particular patient, we have the term post-stroke cognitive impairment. Now, the way to do it is now to use here the right tool for the linking. This is SAP BERT. So we use here a specialized sentence transformer, SBERT, to find here a clean entity in the knowledge graph. How we do this? We calculate simply in the vector space the cosine similarity. This gives us a similarity score. For example, SAP BERT, and we have two terms. We have here our query term, the post-stroke cognitive impairment. And then we have, for example, cognitive dysfunction. And we see, okay, this is a very good candidate that has a very high similarity score. And if we go to the end of the list, we see here two terms that have a very low similarity score. So maybe there's no causal connection between these two terms here in medical. And you see, this is here a negative example. And we will use both of them. So what we have now is a clean unambiguous link from to the knowledge graph node, and now we have cognitive dysfunction. And you understood we started here with the technical term post-stroke cognitive impairment, and now we have here from SBERT here one candidate that is real close by. But now we have also, and remember this was the update process for the knowledge graph. So this means we have now also in the knowledge graph the new node, a precise address in the knowledge graph. And now we query it to retrieve now the structured facts from this node. We follow all the edges to the other nodes. We have a 1-hop or 2-hop or 3-hop sequence. So we extract all this information from the knowledge graph. And we build our triplets. For example, one of the results might be paravastatin not treats here cognitive dysfunction. So our triples, we generate here the update triples for the update here of the knowledge graph. Now, in our example in the publication here, they decided here for medical to go with a 3-agent configuration. The first agent is simply here doing the linkage that I just showed you. The second agent is doing the retrieval if you want the researcher. And then we have an agent that predicts here something. We do AI to have a prediction about the future to discover new facts. So you see, this is the overall picture, how you use here your, if you want, transformer-based LLM as the core of an agent. Then you have multiple agents. And now those agents have a very specific interaction pattern with the updated knowledge graph that is now optimized for your domain. And in order to do so, we needed here a very specific sentence BERT system that we used here as a cross encoder. Or if you go with Colbert here for a search optimization, Colbert is really beautifully fast. But we are looking here for a very particular type. It's not only for search, but it is also here for entity, our NER engine. So here's the official, if you want, visualization here from the paper. So very easy. We have here the medical data here from a very particular patient. And then we have here one question. Will David, this is our patient here, develop here the post-stroke cognitive impairment in the next time? So a very general example. And here you have now our 3 agents. How Emory and Stanford University imagine this. So linked agent, retrieval agent, and then the prediction agent. So let's have a look at this. So at first, the linked agent tells us, hey, I connect the medical entities between here, this what we know about our, if you want, our patient here with the knowledge graph. So as I showed you, we start here with the term post-stroke cognitive impairment. And then we look here for the beautiful candidate. And remember, we needed here also the vector operation, the cosine similarity operation from a sentence BERT system. Then if we all have here the right address here in the knowledge graph, I told you we have positive and negative relations. And now we extract the positive ones and we extract the negative ones. This will help us in the learning process. And then the prediction agent takes now all the information, collects everything up until now, and has a 2-stage process. In the first stage, we have here, I will show you this in 2 minutes time. We generate here a response, but then we have another check, if you want, in the stage 2. And here we can correct here, and this is a beautiful mechanism. So you really find out that the ground truth and the final prediction, they both agree here. Let's have then a look at this. So if you see that those are just 3 agents and 1 knowledge graph, please note, this is not really absolutely correct, because we had to update the knowledge graph via, for example, a sentence BERT system, and we do here the agent interaction also via an SAP BERT system. So let's have a look. So the linked agent, simple, no? As I showed you, the term post-stroke cognitive impairment here using SAP BERT finds here the closest entity in the knowledge graph here, calculating here cosine similarity, and we know now this is the node that we have to look for in the knowledge graph. This is cognitive dysfunction. Then the retrieval agent, easy, no? Goes here to the knowledge node cognitive dysfunction and queries now the knowledge graph. Goes all and the edges, follows here 1-hop node, 2-hop nodes, and we collect the positive and the negative relations. So we have 2 lists, a good one and a bad one. Then the prediction, as I told you, we have two stages. At first, we take only the positive knowledge. So here is now that we have maybe too much of a positive vibe, and we do not have enough of contra knowledge to limit here, if you want here, the knowledge space. So it could be that we come here, or the agent comes here to an incorrect answer. And therefore, the authors of the study said, hey, we have a stage 2, which we call kind of a correction, you know? So we take everything from the stage 1, and maybe we overshot a little bit with our optimism, and now we add the negative knowledge. And you guessed, this is beautiful, this brings us back on our path, and now we have, hopefully, a correct prediction. You see, the idea is rather simple. And of course, if I talk to you about a knowledge graph, the structure, you know this is a network of nodes, of entities and edges, the relations. Now, in the concept, I always show you a two-dimensional representation, but of course, mathematically, it's formally a non-dimensional, because a graph, mathematically, a graph is just a set of vertices and a set of edges. And topological, it's about connection and not about coordinates in space. So it has, if you want to be more precise, no inherent dimensionality. But we have to calculate with those. We have to have numerical calculations. So what we do, we take the knowledge graph and we do an embedding. We do a machine learning representation. And guess what? We go in the simplest mathematical space available. And this is a vector space again. So we have now a very high dimensional vector space, 768 dimensions, and we build vectors for everything that we find in our knowledge graph. And then we can, if you want, enable now the mathematical reasoning, the operation that we have in a vector space. We can do similarity search. And then we have here the learning process for a real AI model. And the training is happening now really in a way that if we have a particular vector here from, if you remember the triplet here from the first term, plus the vector from the relation term equals then this term. If we have here a training experiment that this is a vector representation, we get that is learned beautifully. If you want to have a closer look at the agent now, of course, and you might ask, so wait a minute, this agent is now operating on a vector space, or is it operating in the human linguistic space of our words? Now, interesting, the linked agent is a translator and it has to be fluent in both worlds. Must do both, vectors and linguistic. So at first, we operate, as I showed you already 2 times here, in the search process in a high-dimensional vector space with the BERT model. Cosine similarity, we find the knowledge graph vectors, great. And then starts the reasoning. The reasoning is easy. Now we say, okay, we have it, and then we present here the text labels of the top 10 vector candidates that are closest by in the vector space. So we have now candidates that are now in the linguistic space, cognitive dysfunction, memory impairment, or whatever else. So we do have now our top 10, top 100 candidates. With this information, now we can go now to the retrieval agent. So it retrieves now the text from the chosen knowledge graph entities from the linked agent. And now it simply uses these text names to query now the knowledge graph in more depth. And you know, this is a kind of a symbolic database, and it retrieves here the list of factual triplets, as I already showed you. And the output is simply, we have a positive knowledge and a negative knowledge. We already went through this. And the prediction agent finally takes all of this here our patient data, the question, and all the guidance that it got from the knowledge graph. And here in this particular study, the authors used a GPT-4o mini here as the LLM to combine this and have now a reasoning process. And this reasoning process here, integrating all the data, all the information, all the knowledge that we get up until now, and it produces here a text-based answer. Either it's a yes or a no in the simplest case. And also, if the reasoning is available, a text-based explanation why the AI think that this is the correct prediction. Now you might say, hey, let's benchmark this. No? And there are a lot of other possibilities we could have done this. No? We could have gone with directly prompting the LLM here with the patient's data. No construct of knowledge graph, no multiple agent, just go and prompt it with one LLM. Or you could say step-by-step prompting, ne? Prediction steps, and we use something like a chain of sort. And then you say, you know what? In, let's say, a medical research, I'm sure they'll have pre-trained, highly dedicated medical large language models like this one here. So let's use here the medical LLMs that were trained for this particular purpose. Or you go and say, okay, I just do now a knowledge augmented prompting. And there are also some methods available in the medical databases. Or you say, you know what, I go with iterative prompting. So this is more or less here also what we just went through in the last 10 minutes. But we do not provide information from the knowledge graph. Otherwise, it is everything identical, but no info from the knowledge graph. So we see how important is here the correctness, the additional data, the structured knowledge that we get here out from a knowledge graph. Yeah, so let's have a look. And here you have the data. So here you have all the methods we just went through. And here in the last line, KERAP is here the methodology that we focus on today. Now, you have different benchmarks, beautiful from the medical team. But I think you see that, let's just look here at the first one, 21, 22, 28, 27, 24, and 72. So the authors are quite proud here on their achievement. They say, hey, our system is really looking great if you compare it here to other systems. And they even say, hey, we even can give you a guidance here how much it costs here for these diagnosis prediction methodologies that we have. And again, here are different alternatives. And here in the last line, KERAP here, the topic of this paper. And you see, yes, it costs here really quite a lot of. It is more expensive than any other methodology. And you might say, of course, no? I have 3 agents that interact in some non-trivial ways with specific vector operation, with specific knowledge graph operation. So yeah, you generate here, if you just look here at the tokens that you need here for the procedure and for the reasoning and for the data aggregation here, and this is here in millions of tokens, you see that KERAP here, for example, the authors tell us, they need 72 million tokens to run through one diagnosis prediction. So, real nice, give you the token, give you kind of the cost, give you, the time, depends on the infrastructure, and so on. If you want to see this in color, please here, this is for the different benchmarks here, you see again all the different methods in here, again KERAP here, the method of this paper here, you see in this violet, and as you see, it's simply outstanding here of the performance, and they used here a GPT-4 Omni. In the end, I give here the word also to the authors, and they say, we propose here KERAP, a knowledge graph enhanced reasoning framework for zero-shot diagnosis prediction using our LLMs. We address here the key challenges in LLM-based medical diagnosis that we have today, including the need for more structured reasoning, a reduction in the hallucination, and an improved effectiveness for the clinical environment. And by integrating here a multi-agent framework consisting now of a linked agent, a retrieval agent, and as I showed you, the prediction agent, this combination connects here the patient data with structured medical knowledge and refines its diagnostic reasoning through multi-stage conversational steps. Experiment results demonstrate that KERAP enhances the diagnostic accuracy compared to existing methods effectively and efficiently. Real nice, really interesting, but never forget the methodologies in the simplest explanation is more or less always the same. We operate either with encoder-only blocks, with decoder-transformer blocks, we operate in vector spaces, or we use here self-attention mechanisms. Plus, we use here optimization, we use fine-tuning, reinforcement learning, we build better knowledge graph, and then the actions that is happening is simply when our agents interact now with the parametric knowledge of an LLM within an agent, with here the structured knowledge representation of a knowledge graph. But we need to go through here for the vector operation through a particular constructed vector space, high-dimensional vector space that we have here in Sentence BERT. So you see, it's always the same components that are here in play, but given that this was published here just 2 days ago by Emory and Stanford University, I think they provide here a beautiful explanation how we can combine for real safety-critical tasks in a clinical environment. What is the best way to combine LLMs, agent, and knowledge graph? I hope you enjoyed it, and if you want to see more of those videos, why not subscribe, and I see you in the next one.